Imagine a world where distance is no barrier, where information can travel instantaneously. What if I told you teleportation is real? It's not just a figment of sci-fi imagination but a tangible phenomenon actively being explored and refined in cutting-edge laboratories today. Scientists are pushing the boundaries of what we thought was possible. Scientists have achieved the seemingly impossible. They've teleported information instantly from one location to another. This isn't about physically moving an object, but rather transferring its complete quantum information without it actually traversing the space in between. It's like sending a fax of reality itself. This mind-boggling feat is made possible thanks to the strange and counterintuitive laws of quantum mechanics. These laws govern the behavior of matter and energy at the atomic and subatomic levels, and they often defy our everyday experiences. This isn't some parlor trick or illusion. It's a genuine, verifiable effect, a real-world phenomenon that profoundly challenges our fundamental understanding of reality and the very nature of the universe. When we hear the word teleportation, our minds often conjure up images from Star Trek, with beams of light and matter dissolving and reforming elsewhere. But the real achievement in quantum teleportation is far subtler, and perhaps even more profound in its implications. It's a quiet revolution happening at the smallest scales. Instead of physically moving matter from point A to point B, we're actually moving the quantum state, the complete blueprint, the entire set of information that defines a particle. And in this process, the original particle is effectively destroyed, its information perfectly copied onto another particle at a distant location. While we can't teleport people or everyday objects just yet, that remains firmly in the realm of science fiction. The underlying principle has been rigorously proven through countless experiments. This groundbreaking breakthrough represents a foundational step toward developing revolutionary technologies that could fundamentally redefine the way we communicate across vast distances, the way we approach computing, unlocking unprecedented processing power, and the way we conduct space exploration, pushing the boundaries of scientific discovery. Ultimately, quantum teleportation is providing us with invaluable insights into how we might one day learn to manipulate the very fabric of reality itself. The journey begins in the enigmatic quantum realm, where the seemingly impossible becomes not only possible, but a demonstrable reality. To truly understand the fascinating concept of quantum teleportation, we need to shift our perspective a little. It's not about what you might initially think, like beaming people or objects across vast distances as seen in science fiction. The reality, while still mind-boggling, is far more nuanced and revolves around the peculiar laws that govern the quantum world. So, let's momentarily forget about the idea of physically moving objects from one place to another. Forget about disassembling something here and reassembling it perfectly somewhere else. That's not what's happening in quantum teleportation. Instead, think about the movement of information itself. Think about how data can be transmitted, copied, and recreated without the original physical form ever leaving its starting point. This is closer to the heart of quantum teleportation. To illustrate this, imagine Alice possesses a unique and intricate Lego sculpture, a one-of-a-kind creation that she's very proud of. Now imagine Bob is located far, far away from Alice, but he happens to have an identical collection of Lego bricks at his disposal. He has all the necessary components, but lacks the specific arrangement, the blueprint, to build the same sculpture. Quantum teleportation, in this analogy, is like instantly transferring the exact arrangement of Alice's Lego sculpture to Bob, allowing him to build an identical copy. It's about sending the instructions, the precise configuration. However, there's a crucial catch. This process involves destroying Alice's original Lego sculpture in the process. The original arrangement is lost as the information is transferred. Now, let's bring this back to the quantum realm. In quantum terms, instead of Lego sculptures, we're talking about sending the quantum state of a particle. Crucially, we're not sending the particle itself, just its state, its properties, its characteristics, its complete quantum description. This remarkable process relies on a specific set of ingredients, 3 key elements that work together in a delicate dance. First, we need the original particle whose quantum state we want to teleport. This is the particle that holds the information we aim to transfer. Second, we need a pair of entangled particles, a phenomenon unique to the quantum world. One of these entangled particles is held by Alice, and the other is held by Bob, regardless of the distance separating them. And third, we need a classical communication channel, a standard method for sending information like a phone line or the internet. The process begins with Alice performing a special joint measurement on the original particle and her entangled particle. This measurement has a peculiar effect. It destroys the quantum state of Alice's original particle, but simultaneously alters the state of Bob's entangled particle. Alice then needs to communicate the results of her measurement to Bob using the classical communication channel. Upon receiving this information, Bob uses it to perform a specific transformation on his entangled particle, carefully adjusting its state. This transformation effectively turns Bob's particle into an exact replica, a perfect copy of Alice's original particle. In essence, the quantum state, the information that defined Alice's particle, vanishes from its original location and reappears in Bob's particle. It's important to reiterate that no physical matter has traveled between Alice and Bob. Only information has been transferred. Importantly, the classical communication step means that this process doesn't allow for faster-than-light communication, respecting the fundamental laws of physics. What's truly remarkable is that it's a perfect and lossless transfer of quantum identity. The new particle embodies the exact quantum characteristics of the original. Ultimately, quantum teleportation is about moving the essence, the information, the quantum state, and not the substance, the physical matter itself. It's a profound concept with potentially revolutionary applications in quantum computing and communication. At the heart of quantum teleportation lies a phenomenon so bizarre, so counterintuitive, that even the great Albert Einstein struggled to wrap his head around it: quantum entanglement. It's a concept that challenges our everyday understanding of reality, suggesting connections that transcend space and time. This is what Einstein famously called spooky action at a distance. He coined this term to express his discomfort with the implications of entanglement, a concept that seemed to violate the principles of locality and causality that he held dear. To illustrate this spooky action, imagine two magical coins. These aren't ordinary coins, they're linked in a mysterious way. If you flip one and the other instantly shows the opposite face as if connected by an invisible thread. It's an instantaneous correlation, a perfect mirroring of fates. And here's the truly mind-bending part. This happens no matter how far apart they are. Whether they're separated by a meter, a mile, or even light years, the connection remains unbroken. In the quantum world, entangled particles share a single, unified state. They are inextricably linked, their fates intertwined. Measuring a property of one entangled particle instantly determines the corresponding property of the other, regardless of the distance separating them. It's as if they're communicating faster than the speed of light, a concept that initially baffled physicists. This instantaneous correlation is the essence of spooky action at a distance. Einstein found this idea deeply unsettling. He thought this instantaneous connection was impossible, a violation of the laws of physics as he understood them. He suspected that there must be hidden variables, some underlying mechanism that explained the correlation without requiring faster-than-light communication. However, a series of ingenious experiments inspired by Bell's theorem have repeatedly proven him wrong. These experiments have confirmed the reality of quantum entanglement, demonstrating that the correlations between entangled particles are indeed stronger than any classical explanation can account for. The quantum world isn't like a pair of gloves placed in separate boxes. In that scenario, each glove has a definite property, left or right, before you open the box. In the quantum realm, the properties of entangled particles aren't set until the moment they are measured. It's the act of measurement that forces them to choose a state, and that choice is instantly reflected in their entangled partner. This spooky action, this instantaneous correlation between entangled particles, is the very resource that powers quantum teleportation. It's the key to transferring quantum information from one location to another. Alice's measurement on her entangled particle instantly affects the state of Bob's entangled particle, creating a correlation between their measurements. This happens no matter the distance separating Alice and Bob. The connection is instantaneous, transcending the limitations of space. However, it's crucial to remember that the classical information Alice sends to Bob via conventional communication channels is absolutely essential for Bob to complete the teleportation process. This classical information acts as a key, allowing Bob to decode the quantum information he has received. Entanglement is a non-local connection, a link that exists outside the bounds of our classical understanding of space and time. It's a phenomenon that defies our everyday intuition. It's not magic, despite its seemingly impossible nature. It's a fundamental aspect of the quantum world, and it's the very foundation upon which quantum teleportation is built. The dance of entanglement, the intricate choreography of quantum particles, is both beautiful and profoundly strange. It reveals a universe far more interconnected and mysterious than we ever imagined. This is how quantum information leaps across space without actually traversing it, a testament to the power and strangeness of the quantum world. It's a glimpse into a reality where the rules are different, where connections are instantaneous, and where the impossible becomes possible. What began as a thought experiment is now a routine high-tech lab procedure. China's Misia satellite teleported quantum states between Earth and space, proving entanglement can survive over vast distances. This shattered distance records and showed a global quantum network is possible. In the US, scientists teleported quantum information over 44 kilometers of standard fiber optic cable, using existing infrastructure. These experiments all rely on entanglement, precise measurements, and classical communication. Each success brings us closer to practical quantum networks. We're no longer asking if teleportation is possible, but how far we can push it. The age of engineered spooky action has begun. If we can teleport a photon, why not a person? The answer is complexity. A photon state is simple. A human has 7 octillion atoms, each with its own quantum state. Storing and transmitting that much information is beyond any conceivable technology. Even if we could, the Heisenberg uncertainty principle means we can't perfectly scan every atom without destroying crucial information. The act of scanning would obliterate the very data needed for teleportation. The challenge isn't just technical, it's fundamental physics. Teleporting a person isn't just harder than a photon, it's a different kind of problem entirely. The difference is like sending a single letter versus every book ever written, all at once. For now, human teleportation remains science fiction. Suppose we could teleport a person, scan every atom, transmit the data, and rebuild you on Mars. The original is destroyed, the copy is perfect. Is the person on Mars still you? The quantum no-cloning theorem means only one version can exist. The original must be erased. Would you step into the teleporter knowing you'd be annihilated and recreated? The replica would have your memories and feel like you, but the original is gone. Is this travel or a high-tech copy and delete? Quantum teleportation forces us to question if we are our matter or just the information it encodes. The answer isn't scientific, it's philosophical and deeply personal. While human teleportation is fantasy, quantum teleportation is revolutionizing secure communication. Quantum channels can detect eavesdropping. Any interception disturbs the state and is immediately noticed. This offers security guaranteed by the laws of physics. Looking ahead, teleportation will enable a quantum internet, linking quantum computers and sensors worldwide. Instead of just bits, we'll transmit qubits, delicate quantum information. This network could allow distributed quantum computing and ultra-secure links across Earth and into space. Quantum teleportation isn't about moving people. It's about moving the data that will power the future. The quantum internet is coming, and it's built on teleportation. Science fiction imagines teleporters that dematerialize and rematerialize people instantly. In reality, the challenges are immense. Storing the quantum state of a human is impossible with current or foreseeable technology. The energy required to convert a person to pure energy and back would be catastrophic, far beyond our control. Biological complexity adds another layer. Life is a dynamic process, not just a static arrangement of atoms. Any error in reassembly could be fatal. Sci-fi gets the what right, instant travel, but ignores the how. Real quantum teleportation is about moving information, not matter. The transporter dream will likely remain fiction, but the real science is just as thrilling, because it's happening now. We're opening doors to possibilities even sci-fi hasn't imagined. Quantum teleportation is already reshaping our world, not by moving people but by moving information. The dream of instant travel is distant, but the transfer of quantum identity is real and revolutionary. We're building a global quantum network, secured by the laws of physics. This will link quantum computers and sensors, tackling problems once thought impossible. The quantum realm is stranger than fiction, and we're learning to harness its power. Scientists are explorers, charting new territory in reality itself. The story of teleportation shows how wild ideas become real technology. The future isn't just coming, it's being teleported into existence.